morning. Today we'll be talking about the linear momentum portion of Physics 1. Momentum is one of those few physics concepts where its formula is its definition. Let's begin. Momentum. The formula for momentum is mass times velocity. It's also its definition. It is denoted by the letter P, not the Greek letter rho, and as you can tell from these arrows, it is a vector. Based off its formula, we can tell that its units are kg times meters per second. Now, let's do an example together. A 2.94 Newton ball travels with a velocity of 108 kilometers per hour. What is its momentum? Well, let's see. Recall that momentum is in the units of kg meters per second. So first, let's convert the 2.94 newtons into kg. So we take 2.94 newtons, divide by the acceleration due to gravity on Earth. Yep, we're assuming this is on Earth. 2.94 divided by 9.8, 0.30 because sig fig, 0.30 kg. So, good, now that we have kg, however, the kg, that's correct for the mass, but not for velocity. So let's figure out how to convert velocity into meters per second. We have 108 kilometers per hour. So let's convert kilometers to meters. There are 1,000 meters in 1 kilometer. And furthermore, there are 3,600 seconds in 1 hour. We gotta put the 3,600 in the denominator. 1 hour divided by 3,600 seconds. Based off this, if we use a unit analysis, we see that the km's cancel out and the h's cancel out. So the shortcut for this, you can literally just divide by 3.6. Therefore, we get a velocity of 30 meters per second. Good. So now that we have all the right numbers, let's figure out what the momentum is. Recall that momentum is mass times velocity, so it'll be 0.30 kg multiplied by 30 meters per second. Therefore, we get 9.0 kg meters per second. Alright, so let's talk about what happens when momentum changes, when momentum is not constant. This is where we come to impulse. Impulse is change in momentum, and let's derive the equation. So, to derive the equation for impulse, we use Newton's second law. Recall that in my dynamics lecture, we talked about the fact that Newton's second law is F net equals ma. And recall from kinematics that a acceleration is change in velocity divided by change in time. Therefore, we can substitute a with delta v over delta t, and then if we multiply both sides by delta t, we get that F net times delta t equals m delta v. And notice how m delta v is just change in momentum. Or as we denote it in physics, we use J to denote F net times delta t, which is impulse. But what happens if the net force is not constant? What if it changes? This is where calculus comes in. If you don't understand calculus, that's okay. You will one day. Impulse is the integral of net force with respect to time. Furthermore, net force, if we differentiate both sides, the integral here will cancel out. Therefore, we get that the derivative of momentum, or impulse, divided by the derivative with respect to time, so dp divided by dt, will equal to F net. Alright, so now let's do an example together. Suppose a ball was traveling with a velocity v0 and had a mass m. A few seconds later, it bounces off the wall, but now with double its initial velocity in the opposite direction. What is its impulse? Well, in this case, since we don't know what the time or net force is, but we are given the velocities and the mass, we can use the equation m delta v. So let's figure this out. Change in momentum equals to the final momentum, in this case negative m times 2v initial. Let's make that a little neater. 2mv initial minus mv initial. So now, continuing on, we can factor out the m's as they are the same. So we get m multiplied by negative 2v initial, or v0 in this case, minus v0. doing basic math, we get that delta P equals to m multiplied by negative 3 v initial. So this tells us that its change of impulse, the impulse or change of momentum, has 3 times the velocity that it initially had, but in the opposite direction, as you can tell from this negative. In this case, and because momentum is a vector when you say the direction, this will be going west based off this diagram. Alright, so now let's talk about something that's a bit new. Conservation of linear momentum. Like conservation of energy, which we will learn next time, it states that momentum is conserved within a closed system. So basically there's no net force. The net force is 0. No net forces are acting on any objects. So let's do an example. Suppose this is an electron and this is a proton. Suppose they travel with the same velocity, but one's going in the negative direction, as you can tell here, one's in the positive direction, and then post-collision, they bounce off each other. But the electron goes in the opposite direction and has double its initial velocity. What is the final velocity of the proton? Let's figure that out. So we get that we're going to treat east, or going to the right, as positive and going to the left as negative. So even though the masses here are constant and we're given the masses usually, we don't need the masses as we're just deriving an equation for the final velocity of the proton. Let's figure this out. So MP, mass of the proton, times its velocity, v initial, and remember we're treating right as positive, and plus ME, E being for electron, multiplied by negative v initial, negative because of direction. This is the initial momentum within the closed system, equals to MP times v, which is what we're solving for, v here, plus, negative v because it's going the opposite direction, plus ME times 2 v initial. Good. So let's isolate for v here. You can factor out this negative distributive property, therefore you get that the momentum, the initial momentum of the proton minus the initial momentum of the electron equals to the final momentum of the electron minus the final momentum of the proton. And like I said earlier, we're isolating for this v. So let's see, we can subtract the final momentum of the electron on both sides. So therefore they cancel out here. And then we get that MP, and let's combine like terms. I can see here they are the same. So the initial momentum of the proton minus 3 times of the initial momentum of the electron equals to the negative of the final momentum of the proton. So we're isolating for v. Divide both sides by the negative mass of the proton. Therefore, we get that the final velocity of the proton equals to the initial momentum of the proton minus 3 times the initial momentum of the electrons. I apologize for here, by the way, this should have been in the subscripts, divided by the negative mass, the negative of the proton's mass. But here, since we don't want negatives in the denominator, we can factor out a negative on the top to make things simpler. So now that we get 3 times the initial momentum of the electron minus the initial momentum of the proton divided by the mass of the proton. And it's positive because we factor out a negative here and the negatives will cancel out. So this is our final equation for the final velocity of the proton. So now let's talk about the types of collisions. There are 3 types of collisions in physics. So there's elastic collisions, inelastic collisions, and perfectly inelastic collisions. Let's talk about the difference between the 3. So elastic collisions, which note right now that it never happens in real life unless it's with like particles under a microscope, such as 2 electrons or 2 protons. Inelastic collisions there's zero kinetic energy loss, hence you can see why I'm saying that it never happens in real life. What happens is the two masses go towards each other and then they bounce off in the opposite directions. So let's talk about inelastic now, which is the one that happens the most in real life. The two masses, they collide together and then they go in the same direction afterwards. So yes, there's kinetic energy loss. However, unlike perfectly inelastic over here, it's not the greatest kinetic energy loss. And the reason is, if you look over here, the masses stick together post-collision, resulting in the greatest kinetic energy loss, as kinetic energy, as you can see I'm writing right now, equals to half multiplied by the mass multiplied by the speed squared. We don't need to say velocity because in energy, direction is irrelevant. It has no significance, futile. Anyways, due to an increase in mass and the kinetic energy always being constant, to compensate for an increased mass, you must decrease the velocity. Hence, this is the greatest kinetic energy loss. What happens to the energy, you may ask? Well, conservation of energy. Energy cannot be created or destroyed, but rather transformed in different versions. As you see from here, sound energy and heat. So, and please, one important note, in all three of these collisions, momentum is conserved. There is no external net force acting on either R. If it were, we would have to include impulse and it'd be more complicated. So now let's do an equation together. Suppose a ball of having a mass m1 travels at a velocity v, and it collides with a ball that has a mass of m2, which is at rest, as you can tell from v initial being 0. Post collision, this happens to mass 2, and this happens to mass 1. Let's determine the velocities. And also let's determine if this collision is elastic or inelastic. So if we look at our final velocities, I see that I can split these into components. So the horizontal component, let's find the sum or the sum of the components. So the sum of the horizontal velocities equals to v1 cosine 30 degrees, where cosine 30 degrees is root 3 over 2, plus where cosine 45 degrees is the same as sine 45 degrees, which is root 2 over 2. So that's the sum of our horizontal component for velocity. Now let's talk about the vertical component. Vertical component v sub y equals to v1 sine 30 degrees, where sine 30 degrees is 1 over 2, and plus the negative, or to make it simpler, subtracted by v2 sine 45 degrees. Now, let's add these all up to find velocity 1. Recall that I said cosine 45 equals sine 45 degrees, which is both root 2 over 2. So if we added these up right now, these two would cancel out. The masses will cancel out. Makes my life so much simpler. So now, the reciprocal, if you multiply this by its reciprocal, it's going to cancel out, but not on this side. Therefore, we get that the left side will get 2 times the initial velocity divided by root 3 plus 1. So that's the equation for our first velocity. Now, we use basic algebra. Let's plug this back into either equation to figure out what the second velocity is. So we get that 2v divided by root 3 plus 1 times cosine 30, which is just root 3 over 2, plus v2 cos 45, equals to the momentum, the sum of the momentums. Masses cancel out, and then if we isolate for v2 equals 2. The 2's cancel out here. Let's make this simpler. Minus root 3 times the velocity divided by cosine 45 degrees multiplied by root 3 plus 1. So let's further simplify this. V2, the final velocity of the second object over here, equals to, let's factor out a V, we get 1 minus root 3, which this will result in a negative, because root 3 is greater than 1, all divided by root 3, apologies, this is going to be very small to read, root 3 over 2, multiplied by root 3 plus 1. So let's simplify this complex fraction. What we can do is we can multiply both sides by 2 over 2. And the reason is, the 2's will cancel out on the denominator and we'll get 2 on top, therefore getting rid of the complex fraction. So then we get 2v multiplied by 1 minus root 3, we're not going to factor out the negative this time, it's unnecessary, divided by, let's distribute this distributive property, we get 3 plus root 3, so let's do that, 3 plus root 3. And this is our final velocity for the second object. Now let's figure out whether the collision is elastic or inelastic. So K naught is our initial kinetic energy, and the only velocity that's intact is the velocity of mass 1. This second kinetic energy, this is 0, as it has no velocity. Well, let's figure out let's call this K prime. K prime is the kinetic energy of the final objects. So direction, like I said earlier, it really doesn't matter when it comes to energy. It's futile. So let's plug in what we have. K prime equals to half times the first mass multiplied by V1, which is 2V divided by root 3 plus 1. Furthermore, we add the second kinetic energy, because now this mass 2 has kinetic energy now. So it'll be plus what we have here for V2, 1 over 2, M2, multiplied by 2V, multiplied that. But now that I just saw that 2, I noticed that the 2's cancel out. So then we'll get M2 multiplied by V multiplied by 1 minus root 3, all divided by 3 plus root 3. Now, I just realized I forgot to assign masses for here, but that's okay. So let's figure out how this would be elastic or inelastic. In order for it to be inelastic, K prime must be less than K naught. Therefore, the initial kinetic energy must be greater than all this. And I also noticed just now that the 2's here cancel out. Therefore, we get M1 times root 3 plus 1 plus M2 multiplied by V multiplied by 1 minus root 3, all divided by 3 plus root 3. So this here, the initial kinetic energy, must be greater than the sum of this. There's also one more example that I want to do, which usually you probably won't learn in Physics 1. In an explosion, let's say we had a mass M. What happens is, a few seconds later, it explodes into, it doesn't have to be 3 equal pieces, it's not always 3 equal pieces. It basically just explodes into multiple pieces. So like M1 plus M2 plus M3 plus dot dot dot, meaning you get like as many as possible. So this I like to call sigma m, the sum of the masses, and then it becomes that. Now, what type of collision is this? I know, it's pretty confusing, right? It's surprisingly inelastic. It's an inelastic collision. It loses kinetic energy, but not the greatest. And at the same time, it doesn't not lose kinetic energy. So let's do an example together with explosions. Let's say this was my brain. and it has a mass capital M. Eventually, some students aggravate me to the point where my brain just explodes into 3 pieces. Now, let's see what happens. The first piece of my brain has a mass of 3m and has a velocity of 2 meters per second. 2 meters per second. 2 meters per second east. The second piece of my brain, let's just call it M, it explodes and travels 1 meter per second west. And the third piece of my brain, 2M, goes at 6 meters per second east. So, actually, let's make this a little more interesting. What is the final velocity of the brain with twice the mass of this? So let's see. Remember conservation momentum? The sum of the initial momentums must equal to the sum of the final potentials. The momentum, apologies for my illegible handwriting, but basically sigma p initial must equal to sigma pf. And let's write it out in equation form. Sigma mv equals to 3m multiplied by 2 minus, because of this, and this goes in the opposite direction, minus m plus 2mv. But note, this brain of mine is at rest. So the velocity is 0, and anything multiplied by 0 is 0, students. So we get that 0 equals 2. Let's factor out the m here. Multiply by 3 times 2 equals to 6 minus 1 plus 2v. So we can divide both sides by m, which will result, divide anything like 0 divided by anything is still 0. Therefore we get that 0 equals to 6 minus 1 plus 2v. Let's make this simpler. 6 equals to 5 plus 2v. And then negative 5 divided by 2, because we move the 5 over here, it becomes a negative. Then we divide both sides by 2 to isolate for v, equals to v, or negative 2.5 meters per second. In physics, we don't use fractions. We always use decimals. Now, what does this negative mean? Well, I treat it positive as my east. Therefore, the negative means west. So our final answer will be 2.5 meters per second west. Which makes sense because we have 2 of them going east, and since momentum is conserved within a closed system, to compensate for these 2 going east and only one of the pieces going west, since this is going east, you must and this is inferior in magnitude to this, you must have this going west to compensate for that. So that brings me to the conclusion of my physics lecture on linear momentum. In my next lecture, we will be talking about work, energy, and power. Be prepared for some linear algebra. I will be throwing some terms in, such as dot product, that one may not understand, but that is okay. I hope you guys enjoyed learning with me as I enjoyed learning with you.